Okay, so hello, I'm Void. In the previous video, we created our first EFI application from absolute zero. We installed the toolchain, set up QEMU, and compiled the code and printed hello EFI on the firmware screen. At the moment, many people think they understand EFI, but in reality, this is only the surface. Today, I want to answer the most important question in firmware, like where does our code actually run? Not how to compile or how to print, but like where, when, and why it executes. If you understand this video, EFI will be better for you and you can just go to the next step. So this image shows the full EFI boot flow. We will not explain everything at once. Instead, we will just move from left to right. So right now, let's start from the very left when we press the power button. Like the CPU does not start Windows or Linux. The CPU starts executing the firmware stored in flash memory on the motherboard. At this moment, there's no operating system, no drivers, no file system, and not even like RAM usable memory. This is the most primitive state of the machine. So the first firmware phase is called security. Like security exists for the only one reason, to start execution safely. In this phase, the CPU is initialized, the execution environment is validated, and the firmware ensures that it can continue securely. Security does almost nothing else. There's no memory allocation, no service, there's no EFI application here. Security only exists to safely move forward. Now, the other one is like the firmware enters the PAE phase. Pre-EFI initializations. This is like this phase exists because of one critical requirement. It is the memory. Without memory, you cannot load drivers, you cannot allocate buffers, and you cannot run complex firmware code. So, main of the PIs is to detect and initialize system RAM. During PAI, memory becomes available and the basic hardware is discovered and the system becomes usable. The pages still does not run or EFI application, so like it only prepares the platform. Think of pre-EFI as the page that says now we finally have memory. Now real firmware can begin. Now we have the DXE area. Uh, Driver execution environment. This is the heart of EFI. In DXE, EFI drivers are loaded, firmware protocols are installed, and service become available. This is where EFI becomes powerful. Instead of one big firmware binary, EFI loads many independent like DXE drivers. Each driver initializes hardware, publish service, and like communicates using protocols. This design makes EFI modular and extensible. If you want to become firmware engineer, this phase is where you must focus, and like in other videos, I will explain them and dive into the DXE, EFI application, secure boot, and much more things. Almost everything is interesting happens here. Now, the boot device selection. During DXE, EFI provides boot service. Boot service are function like exposed by the firmware to help code run before the operating system starts. For example, boot service can allocate memory, locate protocols, load images, and delay execution. When your EFI application calls allocate pool like the malloc or locate protocol, that you will learn later, it is using boot service, like you are printing something like hello EFI. Anyways, boot service are temporary. They exist only until the operating system takes control. After that, they disappear forever. Now there's this runtime. UEFI also provides runtime service. Like these are different. Runtime service remain available even after the operating system starts. Examples include like reading the time, managing UEFI variables, and resetting the system. Runtime service exists because the operating system sometimes needs to talk to firmware. This separation is intentional, like after the exe finishes, UEFI enters BDS. BDS stands for boot device selection. Let's do it again. Like when the DXE finishes, UEFI enters BDS. BDS stands for boot device selection again. This phase decides which device to boot from and which image to execute. This is where UEFI applications run. Your Hello UEFI program from previous video run exactly here. It executes once print text and exits. It's not on driver. Now TCL. Let's zoom in. Okay. So after BDS, UEFI enters TCL. TCL stands for Transient System Loads. Like this phase loads the operating system bootloader and prepares the system for operating system takeover. The firmware is still active, but like its role is ending. Now you don't need to know this too much. It's just loading the bootloader. That's it. Now exit boot service after life, like before giving control to the operating system, UEFI calls exit boot service. Uh, this is the most important call in the entire boot process. After this call, boot service are gone, like firmware memory management stops and the operating system becomes the owner of the system, owner of the like your CPU, RAM, and much more things. Now after line runtime, like after exit boot service, the operating system is running, like after life, before the shutdown. Firmware code is no longer active. This phase is often called afterlife. UEFI is not executing anymore, but runtime service still exists. The operating system can still read firmware time and access UEFI variable and request system resets. Everything else is gone. Now we can finally understand the full picture. UEFI is not magic. It's carefully designed for a sequence of phases. Your code runs only at a specific time in a specific phase under specific rules. Understanding this, like, is the foundation of real firmware development. In the next part, we will break down the EFI system table and see how our code actually communicates. So, hello, converts. In the previous video, we write our first UEFI application and printed hello UEFI on the firmware screen. At the end of the program, I added a 5-4 second delay, and I told you not to worry about it yet, but if you are learning EFI from zero, this delay is actually a very important code because that delay shows us how our code talks to firmware, and communication happens through something called boot service. So what are boot service? Let's start from the absolute basic. If your firmware provides many functions to us, like, for example, allocating memory, waiting time, reading variables, accessing protocols, and much more things, all of these functions are grouped into something called boot service, gBS. So gBS stands for boot service. Boot services are available only while the system is still booting. Once an operating system starts, boot service disappears. We talked that before this video. This is very important and we will come back to this later. So what is gBS again? In code, we usually access boot service using a global pointer called gBS. gBS stands for global boot service. It's a pointer to a table. Inside that table, there are many function pointers. Each function pointer points to a firmware function. So if you are new to pointers, don't panic. A pointer is just a variable that holds an address in that case. In this case, gBS holds the address of the boot service table, like when we write gBS stall, we are accessing a function inside that table. So we are not calling our own function. We are calling function implemented by the firmware. So why is gBS global? You might ask, why is that global? The reason is simple. The system table is very large, like pasting it everywhere would be messy. So EFI gives us global shortcuts, like gBS is one of those shortcuts. Now that we know what gBS is, let's look at the function we already used, the delay. I will open VMware Ubuntu. So before that, stall pauses execution. It tells the firmware stop everything for a specific amount of time. Like stop the firmware for 5 seconds. It will completely froze it. No codes, no extensions, no executors, nothing else. Just freezes for 5 seconds or something. This is not an operating system sleep function. Like in C we have sleep, but this is not that. This happens before any OS exists, operating system exists. The firmware itself is waiting. So the time units for stall is microseconds. One is 1 million microseconds, but we won't use it. So if you want to wait 5 seconds, we multiply 5 by 1 million, but we are not going to do that. Okay then, so let's do our first stall. Like I will say, okay, includes, bro, just efi.h. Oh, by the way, wait. In the adk2 folder, create a folder called .vscode, and in the C++ properties JSON, in here I will share this with you. Like like I mentioned this UEFI, I named this UEFI, but you can do anything else. So you can just change this if your folder called something else. So because that's like when this doesn't have in here, it's main.c won't open like uefi.h or something, and it will give error to us. But now as you can see, it's not giving us any errors. So okay, I will just start coding. I will say include uefi.h, then include library file lib, and finally library again, table lib.h. Okay, then after this I'll say EFI status, then EFI API, heart of the UEFI, then EFI main. What just happens in this? I will explain them all later for the other videos, but for now I will explain the gBS format in this video. Now I will say print hello EFI. We can just say that waiting for 5 seconds. Then gBS stall 5 multiply and multiply again. Then we can say prints. We can say goodbye EFI and return EFI success. Why is it giving? Okay, it's not giving us error anymore. Okay, so we will build it now and test it. I will just copy and paste them. I don't wanna just like, write all of them. Okay, so it's done in the UEFI and adk2 folder. Box EFI. I will copy this and paste it on here. And I will open terminal in here. Then copy the UEFI app as root x64.efi and launch the camera. As you can see, hello EFI waiting for 5 seconds. It will just wait for 5 seconds and then it will say goodbye and exit. As you can see. Yeah. So for better things, we can just do for loop, but in EFI we can't just say integer or float things. It's just different. I will explain them all. So let's understand this slowly. I will open the VS Code again. So yeah, this gives us access to the global gBS pointer. These all. Uh, Without it, the compiler would not know what gBS is. Here we call gBS stall, as you can see here. So this jumps into the firmware code. This firmware, like the firmware pauses execution. After the time passes, execution continues. For a real life analogy, like think of it like this: your code is talking to the BIOS. You say firmware wait for 5 seconds. The firmware like replies, okay, I'll handle that, and your code does nothing during that time. But remember this, boot service only exists during boots. Once the operating system takes the control, boot service are gone forever. This is why stall cannot be used in the runtime codes, but only in boot service codes. Now we need to ask a very important question. Where does GBS come from? Like where did this come from? Who gives us access to the boot service? The answer is, as you can see in here, pointer system table. Like system table is just every UEFI application starts with the one function. That function is called UEFI main. UEFI calls this function for us, and it passes two parameters in EFI handle image handle and in EFI system table. These both are so important. Without this, there was like no EFI application. So what's a system table? As you can see in here, system table is a pointer. This structure like contains everything from EFI offers. It is the main communication bridge between your code and the firmware. Inside the system table, there are pointers to the other tables. For example, like prints, console inputs, console outputs, boot service like gBS and runtime service. Nothing in UEFI is globally by default. Everything starts from the system table. So why pointer again? The system table is large. UEFI does not copy it. Instead, like it gives us a pointer. This saves memory and keeps things flexible. So system table and gBS connection, let's talk about that. So earlier we used gBS, but now we can explain where it comes from. Inside the system table, there is files called boot service. gBS is just a global pointer that like pointer to that files. So this means gBS comes from system table and boot service. So important mental like model, like you should imagine the system table as a root object. Everything branches from it. If you understand this track, it becomes much easier for like in the files. As you can see, we are waiting it open. Like so there's some root connection that, as you can see, everything is in here. So in the system table, everything is in the system table. As you can see, root folder, home folder, voids, and much more things, boot folder, and much more things is in the root folder. In EFI application, this is the same. In system table, everything is in the system table. Like everything branches from it. If you understand this struct, like EFI becomes much easier. So why EFI looks objects like oriented? EFI uses structures like without function pointers. This looks similar to object-oriented programming. Each struct each struct contains data and functions. That's why like main EFI calls loop like this. Like to like something and then function to something, as you can see here. So this pattern will appear everywhere. So if you lose access to the system table, you'll lose access to the firmware, because Like EFI system table is the most important thing. That's why EFI calls like EFI always starts here. This is the foundation of everything we will do later. So that's it for the video. Today we learned what boot services are and how gBS style works and why the system table is foundation is like why the system table is important, let's say that. If you didn't understand everything at once, that's completely normal. EFI is not a simple thing and you're learning it step by step. If you have any questions, feel free to leave a comment below. Like, I read the comments and I try to answer all of them. I will try to answer all of them. In the next video, we will use the system table to control the screen and understand console output.